the So the important things to see in this policy book are on the first page, the definition of a credit hour in the state of New York. I have been inundated by students in both 113, 114 going, you cannot expect us to do all this homework. I will point out this is a 4 credit hour course, so by definition, I should be providing you 180 hours of lectures and work. So yes, I actually do expect you to do all that homework. That's part of the reason why I set aside those 2 3-hour body doubling work-alongs, because if you have family that thinks that lecture's just lecture and it's 4 hours and whether you need any additional time to study, you can say your mean professor makes you tune in on Tuesday, Thursday for 3 hours, and that gives you a nice little set of 3-hour window where your family thinks you're working with me and I'm the bad guy, and they can be mad at me, not at you. I'm perfectly okay with you using me like that. My mentor did that for me with my family when I first started doing chemistry research. So if you need to use me as an excuse, do it. Okay? Because I want all of you to succeed. I want all of you to make as high a grade as you can possibly make. And I certainly want all of you to pass this course, which is certainly doable. But in order to do that, you really do have to set aside time to study. And I am fully aware that because you guys live at home, that can be exceptionally difficult to do. I'm a member on Facebook of a group called Grown and Flown. These are parents. They're like, my kid lives at home. I'm like, well, and they won't do chores. I'm like, well, that's because they're working 40 hours at school. They're studying. And they're like, they don't need that. I'm like, yes, they do. Quit it. And don't plan a vacation in the middle of the semester because, oh, it's just lectures. You can make it up. No, I cover a chapter a week. Don't do this. Well, you don't know what you're talking about. I'm like, well, I've been doing this for 20 years, but okie dokie. Don't come back to me and say your kid failed at the end of the semester because you planned a vacation in the middle of the semester. So if you need to use me as being a bad guy, you might as well move down. I'm not passing stuff up past the 4th road. There are 30 people. There's easily space in the chairs for 30 people in the first 4 rows. So anyway, if you need to use me as an excuse for time to study, please make use of it. I promise you, most students that do poorly in this course, it's because they don't have 13 hours to give to study. The worst example of that was a student who was staying with her grandparents because they were elderly. So she was commuting to Brooklyn every day after class, commuting back here, trying to stay with her grandparents. She had no time to study, working. And right toward the finals, she had a D, but she's like, I got to have a C. I'm like, because, I've taken this course multiple times. I've really got to have a C this time. I'm like, well, you got to study. I mean, I've told you that. So she finally stood up to her family and said, I got to study. I can't do this week. She made the highest grade on the final exam, and that pulled her up to C. It killed me because that was a student who had dreams of medical school, but in order to do that, you really need an A, B plus A average. And that student had the talent to do it, just no time to study. So if you need to use me in that way, okay? My professor says I have to attend these additional things, study times. And if they contact me and say, is that true? I'll be like, yep, absolutely true. Must study. These 6 hours, absolutely required for the course. I'll lie. I won't say it's optional, okay? Now, this is the course calendar. You, of course, have had access to this course calendar, but this is the printout version of it. That is the course Bible. As I continue to set up the course in teams, as I set up live streams, as I set up assignments, as I set up quizzes, as I set up everything, I will literally have a copy of that in front of me and I will be checking them off. Because That's the only way I make sure that everything goes the way it has to go for you guys to get what you need to get. So in general, that's how that's going to happen. Um, so your data book. So today what we're going to cover is significant figures, units, measurements, unit conversions. And your data book has a significant number of those unit conversions. We're not asking you at this point in time to memorize unit conversions. Why? Why would you? You can look those things up anytime you need it. What you need to know is which unit conversion you need to use. So that's kind of been the principle of how we're adapting this course to teaching is we are adapting it so that instead of focusing on you need to memorize this, 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 and this, it's you need to be able to use. Because as chemists, we look this stuff in tables. We have like a book that's about twice as thick as this called the Handbook of Chemistry and Physics. And it has all of the data that's in your appendix, in the little bitty appendix of this book, except the entire book is those data. And we look it up. But we know what data we're needing to look up. So what we're aiming for now in this course is we're going to give you a data book. That's the same data book you get for your final exam. That's the same data book you get for all of the exams so that you can learn how to look up what you need to look up to answer the questions instead of trying to memorize stuff that you just really don't need to memorize. Now, these are your homeworks and your bonus. At the halfway point today, I will hand those out, and you'll have half the class to work on them. Now, this particular homework and bonus, both of these actually come out of that optional Chem Connections activity book. I pulled this one out of there instead of writing it from your homework because it's just unit conversions, and a unit conversion problem is a unit conversion problem. And like half of what was in the assigned homework was unit conversion problems, so it's going to overlap. The bonus is also unit conversions, so lots of unit conversions. Now, I have been asked this for both 113 and 114. Is there any way we can submit our homeworks electronically through Teams? And the answer is I'm considering it with some caveats, and I'm going to discuss those caveats here. Then I'm going to make a Word document and post it so that you can read them again, and then you're going to have to sign a form saying you agree to those caveats. And if you do all of that, then yes, we can do electronic submissions. Okay? So caveat number one is if you type it, I don't grade it. So if you type the answers to your questions, even if it's an essay question, I'm not going to grade it. I'll just mark it wrong and write a 0 and go on to the next problem. The reason for that is if I provide these things as electronic files, it is no big deal for you to upload them into ChatGPT. Now, I'm going to put some little things there that will hopefully prevent ChatGPT from answering, but I can't guarantee that that works or that you won't find those. So in other words, I'm going to have to trust that you want to learn this material and pass the exam, so you're actually not going to use AI to do your homework. I have to let go of control and trust you enough for that. If you do your homework in this class, I know you did it. If you do your homework at home, I'm having to trust that you are not going to, that siren song, come use me, it'll be so much easier, won't catch you. Now, how can I tell if it does? Well, there's two things. First of all, ChatGPT sometimes lies. Second of all, it works the problems in a very particular formulaic way that most students haven't figured out how to work yet. I sort of work problems the way ChatGPT does. I've been doing this for 25 years. Most students do not work problems that way. Second of all, if you make 100% on every homework and make a 10 on the in-class exam that I also pulled from that homework, I mean, come on, guys. It's kind of obvious. That's in fact how we figured out that we could no longer use online homework systems. So everybody was making 100 on all their online homework. I was pulling the exam straight from that online homework, and the average was a 15%. And I'm like, what the hell? It used to correlate. Students that had 100 on their homework were passing the exams. Now it doesn't. Took one semester. That's all. So I have to allow that trust to happen, and it's been kind of hard because of the rampant use and the rampant cheating and the fact students have been bragging about cheating in the chemistry classes in their other classes. This happened last semester. The people were in physics bragging about how they were cheating in organic. Didn't think that the organic physics professors know the organic professors and reported it. Like, oh, great. So that's part of the reason why trusting is a little bit hard right now for all of the faculty. So hopefully, if you want to do that. Now, the other thing is because you're having to handwrite it, you either have to have the ability to write with your computer. So, for instance, I asked during COVID for a Surface tablet where I could write. They gave me a Surface laptop, which has a great touch screen, but you can't write with the screen up at a 90-degree angle. So I have this wonderful little $40 device that lets me write. And that's what I've been using when I lecture for you guys. If you're using, since I'll probably push this out using OneNote, if you're using a Apple iPad or something like that, you can write your answers in OneNote and submit it. No problem. If you don't have the ability to write, or you're not using tablet, because man, those tablets are expensive. Not all of us have the money for that. If you don't have that ability, what you do have the ability is it will also be linked where you can print it out. You can handwrite your answers on it. And then you can download a free app on your phone that will convert pictures to PDF. What I am not accepting is a 15 separate pictures. If that's what you submit, I'm just going to put a 0 and go to the next student. Because I got to grade it, and I'm not flipping through 15 different pictures and loading them into Photoshop where I can write on them. You see? Not doing that. Now, there's multiple ways you can do this. You can upload your pictures into OneNote and submit the OneNote file. That works. Because then the pictures are in OneNote. If you do it that way, once you've this has been a problem. Once you paste a picture in OneNote, scale it up where it's, standard page width. Look at it, make sure it's readable. So if you're writing in pencil, you may need to darken the picture a little bit. So make sure you can read what you wrote. And then right-click on that picture and tell it set picture to background. What that's going to do is it's going to freeze that picture on the OneNote page. And then you can go down below that and put the next picture in, scale it up, set picture to background. And that keeps the pictures from jumping around. That makes it easier for you to insert the next picture. And just in general makes it easier on you as well as on me. But that's one way to do it. The other way to do it is there's a lot of free apps on your phone that will convert pictures to a PDF file. You can just upload the PDF file. Because I can grade that too. So these would be the conditions, but you would have to understand that if you just send 20 pictures, that's a 0. If you type it, that's a 0. And that'll be written out in the change of policy because I'll update the course assignment policy document to reflect that. So I want you to think about it. I'm not going to ask you to do that right now. I want you to think about it. I'm going to put it in writing. I want you to read it. I want you to think about it. And then if you agree to do that, we'll make that change, okay? And all of that's going to have to happen before Friday because the first homework's due on Friday. So I'll get it written tonight, get it uploaded where you can think about it tomorrow, and you can decide yes or no on Friday, okay? And I might shift the due date to Saturday if it's electronic. If it's not electronic, it would have to be on Friday. Course check-in, the form is available for you to go online and check in and type your name. If you don't want to do that, I can send around a sheet of paper and you can just write your name. I don't I'm not picky which one. Just let me know. So let's talk about unit conversions. Now, well, in order to talk about unit conversions, we have to first talk about the okay, so in order to talk about unit conversions, the first thing we have to talk about is what's the real difference. This board is so tempting. What's the real difference between a number and a measurement? And this is really, really important when you're in the laboratory. So, as a chemist who has done research, when I am applying to get money to do research, the first thing I do is I sit down. I don't really have that idea of hypothesis, as I said, it's not the way we do, but I have a goal. And I know what type of experiments I'm going to need to meet that goal. And then I know what type of instruments I'm going to need to purchase to do those experiments to meet that goal. And when I know that the instrumentation, I kind of know, okay, this is what I would love to have. Because usually when we're designing this, we have not just the goal we want to do immediately, but also goals we might want to do in the future that might use that same instrument. So we're going to try to buy an instrument that will get us through not just one 3-year grant cycle, but multi 3-year grant cycles, because instruments are expensive. We're about to start talking about instruments that are the price of a car, okay, or a house. So instruments are expensive, and you kind of want them to be usable for more than one experiment. But at the same time, you have to justify the purchase of instruments to granting agencies. So if you justify an instrument that's too good for the experiments you are currently proposing, they're going to go, well, why do you need that? I mean, it's $30,000, and what you need is an instrument that's only $10,000. So why are you asking for a $30,000 instrument instead of a $10,000 instrument? So you really do have to have in mind what level. I mean, what's the difference between a $10,000 instrument and a $30,000 instrument? The precision at which it can measure something. Seriously, that's the difference. So generally speaking, once you hit a certain point, the cost of the instrument goes up by 1 order of magnitude per every decimal place you add to the measurement. Yeah. So if I'm looking at, say, a balance, so balances, a little thick. Hey, you. Now, you're going to notice a little bit of lag between this computer and my home computer. My home computer is like an Uber gaming computer, and this is a Microsoft Surface, so be patient with it. So if I'm looking at a balance, now, a balance measures mass. Now, we often confuse mass and weight, but weight has gravity factored into it. A balance, when you purchase it, has a little internal calibration mass that's a fixed mass, like 1 gram. And it is measuring relative to that 1 gram mass. And that's how it accounts for gravity. And you can calibrate it if you need to. And like if you're in Denver or up in the observatories in Hawaii, you're probably going to need to calibrate your balances, because there you're high enough above sea level that even with that 1 gram calibration balance inside it, it's probably not going to be uber happy with you, because it's 2 miles above sea level, and the gravitational constant is significantly different. So when you measure stuff in a chemistry lab, what you really are measuring is a mass, not the weight. And the difference between those two is the gravitational constant. Now, the Here's the next issue. We have a governing body called IUPAC, International Union of something something, it's French. But they dictate things like the rules of nomenclature. What are we going to call standard measurements? At IUPAC and also at Greenwich in England are the standard measurement for mass. And it is a beautiful 1 kilogram sphere that is exactly 1 kilogram. And that's, in the end, if you really need accurate measurements, you can send whatever you've got to them and they will calibrate it relative to that wonderful, beautiful 1 kilogram sphere that has been there for ages. And you have to like put on full bunny suit and gloves and all sorts of things before you're allowed to even pull that thing out. It's in multiple containers because no dust can get on it. It is the standard kilogram. But they had a problem with the standard kilogram recently called it was losing mass. And was losing mass because it's stored in a vacuum chamber under another vacuum chamber, and even metal has a vapor pressure. So you store a 1 kilogram metal ball under vacuum for 100 years, it loses a little mass. Don't think that's a big deal. I mean, it didn't lose much, but this is your standard that you're measuring everything relative to. So it was a big deal. So they're looking about how to adjust standards using maybe the speed of light or some energy because E equals mc squared, but they haven't come up with exactly what they're going to use just yet. But the problem is the standard is 1,000 grams or 1 K gram, where this K stands for 10 to the 3. And in a lab, we don't ever, I mean, we're measuring 1 gram, not a kilogram. So technically in a chemistry lab, our standard mass is a gram, not a kilogram. But the IUPAC standard is a kilogram. So that's one of those instances where there's all sorts of hand waving in textbooks because technically the base unit for mass is grams, but the standard unit for mass is kilograms. You see? So it leads to all sorts of fun ways of justifying that. So a gram, this G, is what's called the base SI unit. But 1 kilogram is the IUPAC, thank you, standard for mass. So that's just one of those things you have to be a little bit used to. Now, there are a whole bunch of base SI units because we got tired of writing times 10 to the 2, times 10 to the 3, times 10 to the 4, times 10 to the 5, times 10 to the 6, and so forth. Not all of those will you need to memorize. And since those apply to both numbers and units, well, they don't. They apply to measurements. So the difference between a number and a measurement is a unit. So if you do not write a unit behind a number, then it's just a mathematical number. And you are free to do whatever you want to with it. If something is a measurement, it has a unit associated with it. And this is a big deal. Because, for instance, I can add 1 plus 1. It's 2. We all know this. I cannot add 1 gram plus 1 milliliter. One's a volume, one's a mass. Those don't add. I can add 1 gram to 1 milliliter, but I can't add 1 gram plus 1 milliliter and get 2 whatevers, because what would it be? So measurements can only be added if the units are identical. So even if I want to add like 1 gram to 1 kilogram, I got to put one of those in the correct units. So the units have to be exactly the same. It can't just be, well, both of these are units of mass, so I can add them. No, they've got to be the exact same unit of mass. Then you can add them. So this is something to be aware of, and this really is a big deal for measurements. The other big deal for measurements is all measurements have error. Math has no error. 1 plus 1 is 2. But if I try to measure 1 gram on a balance and add another gram to that, there's all sorts of errors involved in that. My hand could be a little unsteady and I could spill a little bit of powder on, not on my paper, but on the side of the balance. That's going to put an error in my measurement. The balance could not be calibrated correctly. That can introduce some error in the measurement. So all measurements have a certain accuracy and a certain precision. And those are two different things. One of them you can make adjustments to improve. The other one, the only way to change is by a new instrument. Okay? Because in the end, the instrument is what limits and or determines the accuracy of certain things. And sometimes we use these in different ways, or we use them interchangeably, which can be a problem. So hey, whoa, move down. We're just using the first 4 rows. So precision is, there's 2 different types, okay? And they are somewhat related to each other. But there is what's called instrument precision. That, when you buy an instrument, it comes with that precision. That's as good as it gets. This is basically how many decimal places the instrument can measure to. So, going back to our balance, I can have a 1 gram balance. I can have a 0.1 gram balance. I could have a 10 gram balance. That would be if you're in haulage, like grain trucks. I could have a 0.01 gram balance. This is also called a 10 milligram balance. I could have a 0.001 gram or a 1 milligram balance. I can have a 0.0001 gram balance. This is a 0.01 milligram. And I can do even better than that. The best balance I've ever seen is a microgram balance. Okay? So I'm going to actually do this by just sliding this over just a little bit. So I can have a 0.0000001 gram, which is 1 microgram. Now, the cost of this 10 gram balance, something that's only precise to 10 grams. In other words, if I weigh something, it's plus or minus 10 grams. Maybe $15. Cost of a 1 gram balance, that's maybe $30. The cost of a 0.1 gram balance, maybe, $50. So it's not bad. The cost of a 10 milligram balance, well, here is going to depend on not just the precision, but the accuracy. So I can get 10 milligram balances that will read 10 milligrams, but they're not uber accurate. Or I can get 10 milligram balances that will read 10 milligrams and are uber accurate. So there's a price range here. The price range for a 10 milligram balance is going to be anywhere from $100 to $1,000. So it's really just going to depend upon how accurate. Now, that leads us to, okay, well, what's accuracy? So I've already listed the precision. It's 10 milligrams. That means that's how many decimal places it can read. So if I measure 1 gram, it's going to give me 1.00 grams, 2 decimal places, because it's 10 milligrams. But if I know this is 1 milligram and it reads 1.02 the first time I measure it, 1.05 the next time I measure it, 1.03 the next time I measure it, versus 1.00, 1.01, 1.00, 1.01. The first one with that large variance in that decimal place, that's the $100 version. The second one with no variance in that decimal place is the $1,000 version. Okay? 1 milligram balances, the same thing holds. They're going to be between, on the low end, $1,000. On the high end, a really good, accurate one, $5,000, somewhere in that range. When you get to these sub-milligram balances, this one, I think about the cheapest I've seen it's about $8,000. And they go up to, $15,000 thereabouts. We do have one of these. I've only ever seen 2 balances that were better than 4 decimal place balance. 4 decimal place balances are actually pretty common, but a 5 or a 6 decimal place balance, those are very rare. A 5 decimal place balance, it needs like a really expensive. You couldn't put a 5 decimal place balance on this table because this table's not stable enough. There's too much vibration in this table. It would never, the mass would never stabilize due to the vibration. So you usually buy this really heavy marble table that's like a foot of marble top, a foot of marble for the legs, and that's what you put this balance on, because that's not going to vibrate. You can walk by that marble table and hit it, and it will bruise the bejesus out of your hip, but it's not going to change the mass on that balance because it weighs too much. I've inadvertently bumped into it. It hurt. But I didn't get yelled at for bumping into it because it didn't affect the person who was measuring. This is going to, the one in between here, the 10 microgram one, okay? That one's going to start at 50,000, not counting table. The microgram one, I don't think you can buy it for less than 150,000. So, if you are proposing a measurement where you need milligram precision and you propose to buy a microgram balance, the granting agency is going to come back at you and go, why? Because the cost difference between $5,000 and $150,000 is huge. And so if you need a microgram balance, you better say you need it, and you better justify that you absolutely must have this microgram balance for these experiments, or you cannot do them, because the standard average cost of a National Science Foundation research grant is about $300,000 for 3 years, or $100,000 a year, and about the maximum you can ask for instrumentation is about $200,000. So pretty much the maximum high-end level grant that you can ask for from the National Science Foundation is about $500,000 over 3 years total. And that just ate a lot of your budget, that microgram balance. You see? So you really got to want it, and you really got to need it if you're going to do it. But this is the reason why scientists get so mad at you as freshmen when you're measuring something in the lab. You went to the balance that measures, milligrams. You actually measured really accurately 1.000 grams, and you write 1 gram in your lab notebook and walk off. You just took a $5,000 balance and reduced it to a $20 balance by what you recorded in your notebook. You see, when we read research papers, we can tell just by the numbers reported the equipment that they were using to do those measurements. And that's why, as scientists, we get really, really touchy about precision and always writing all of the numbers your balance gives you. Now, I'm going to yell at you when you write all of the numbers your calculator gives you, because your calculator assumes that everything's measured to 8 decimal places. It doesn't know the precision of your balance or the precision of your volume of your glassware or anything like that. It's just an 8. It gives you 8 decimal places. That's what it's coded to do. You have to know, oh, but my balance only measures to 2, so I can't report this to 8 decimal places. Because if I report to 8 decimal places, I got $1 million balance. You see? So you do need to be very aware of measurements. Now, instrument precision is not something that you can change. You purchase the instrument, it comes with a precision built into it. If you want more precision, buy a different instrument. Now, every instrument you can measure less precision on. But if you need more precision, you have to buy a new instrument. Now, there's another precision, and that's user. So the next standard mistake that a lot of students make in first-year labs is we ask you to talk about the error of your experiment. And you write something like, there was error. Every measurement has error. There was error is kind of an obvious, we're like, yeah, 0. Because we asked you what the error was. We know there's error. What we're asking you is, where is your sources of error? So that precision is user-based precision. Now, for a balance, it's really hard for a person using a balance for their precision to not really match the instrument's precision unless you're in the sub-milligram, microgram balance region. There, you got to be careful. So if you're measuring on a 0.1 milligram balance, the oil on your hands will change the mass. So you don't want to pick up something to look at it and put it back on the balance to measure it again, because the oil on your hands is going to change the mass at that level of precision. If you're measuring on a 0.1 gram, it's not going to detect the oil on your hands. So it is really easy for beginning users, beginning scientists, to match the precision of all the way up to a 10 milligram balance. You don't have to have great technique for that. But when you get to a 1 milligram, a 0.1 milligram, a microgram balance, your technique has to be flawless for your precision in using the instrument to match the instrument's precision in measuring the material. Now, volume is different. Volume takes time to get good at. So in my lab, and remind me, one of you guys pop onto Teams before this class next week and remind me to bring pipetters where you can see them. My lab, we use pipetters. We have a 1 to 10 mil pipetter. We have a 100 to 1,000 microliter pipetter. And we have a 10 to 100 microliter pipetter. I can match the precision of my pipetter in the 1 to 10 mil, and I can match the precision of my pipetter in the 100 to 1,000 microliter. That 10 to 100 microliter pipetter, I will go out of the way to change the concentrations and design experiments where I do not have to touch that thing. I can't use that thing for the life of me and get it and match its precision. My 10 microliters is never 10 microliters, and it's never even consistently like 11 or 12 microliters. It's all over the place. And the reason for that is 10 microliters is not even a drop. I mean, it's like a quarter of a drop, roughly. So if you have any little droplets on like the outside of your pipette that kind of fall in, you're done. If you don't completely dispense everything correctly, if your pipette's not uber clean, your pipette tip, it's not going to be, I mean, there's so many things that impact that bloody pipetter. I'm like, we'll change the experiment where we can scale up the volume to the less sensitive pipette. Now, biologists, pharmacists, they use that bloody 10 to 100 microliter pipetter all of the time. It is like their go-to pipetter for biochemists. And because of that, they're very good at it. They have a lot of practice. So, I could get better at it. I could practice more. But I'm like, why? I only need it like once in a blue moon. I'll just change the experiment rather than sit here and practice for the months it would take for me to get good at using this bloody pipetter. So that type of precision, user precision, can be changed. Practice changes this. So user precision is a measure of the user's ability. I'll use scientists here. By the way, as soon as you guys take a freshman chemistry lab, you are beginning scientists. Don't let anybody tell you different. A measure of the scientist's, we all started somewhere, ability to use the instrument. So anybody, that precision you can improve. You don't have to change the instrument. You can make that precision better to a point. What's the point? To the instrument's precision. When your precision matches the instrument's precision, that's as good as it gets because you can't change the instrument's precision. Now, accuracy is different. And if you're curious, precision and accuracy of anything in chapter 1, if you want to know what is the most important thing out of chapter 1, it's the understanding of accuracy and precision and measurements. And the reason for that is that's important in every science class you take. Not just freshman chemistry. It's important in organic chemistry. It's important in upper level chemistry. It's important in physics, in biology, in neuroscience, and psych. All of those courses rely on you understanding the difference between precision and accuracy. And for those of you that end up in psych and neuropsych, you're going to take a statistics course where you're going to derive the formulas that tell you the difference between accuracy and precision. Okay? We're going to use those formulas in this class, but we're not going to derive them from first principles. But I will point out a place where chemistry measurements differ from psych measurements, because there's a subtle difference in a place. So accuracy. Accuracy you cannot talk about unless you're given a number to compare to. No number to compare to, you can't say anything. I'm trying to be clean on the. You can't say anything about accuracy. So for accuracy, it is how close your measurements are to a number that's given by another lab or another technique or something like that. So this is how close are your measurements to the expected value. Now, the truth is, in most research labs, so many of you will join a research lab at some point, you can't say anything about the accuracy of your measurements. Why? Nobody else has ever done them before. So you don't have a number to compare to. You're the first person to ever measure this. So how do you know it's right? Well, you have to basically done everything you can in terms of your learning of the instrument, in terms of your calibration of the instrument. You have to do everything possible to ensure the precision of your study so that you can then hope that the value that you get is accurate. So sometimes we might do a control. Biology does that a lot because that gives you something to compare to. So then you can talk about the accuracy of your study versus that control. In chemistry, we don't tend to even do that. We just trust. And over time, if your group has been good and you develop a sense of trust within the community, then the community's like, okay, their measurements are probably as good as you can get. And this is a big deal. So like in my field, and in something we'll cover very late in the semester called thermodynamics, there are equations of state. Those equations of state are empirical. They're not derived. We collect all these data from all these different labs that have measured these things, and we fit it to an equation. But when you're doing that, you have to make some judgment about how good the lab's data are. And that's where that sense of trust is. Okay, we know that this group, their data is the best possible data. So we're going to weight their data in our fit higher than this group's data because their data is okay and we don't have the data, so we have to use it because they're the only ones that did it in this range. But generally speaking, their data is not very accurate. So we'll put it there, but we're going to put, if our model doesn't fit that data, that's maybe okay type deal. So, and they tell you this in the papers where they give you the equation. They list all of the places that they pulled data from, and they list how they weighted those data in their final fits. And that's kind of this is who we trust and this is who we don't trust. So it is kind of a big deal for them. But that means in order to talk about accuracy, you have to have something to compare to. So an equation that's going to ask you to discuss the accuracy of something, it's got to give you a number to compare to. In the laboratory, you're going to hit this when you do the hydrate experiment. You're going to be given a copper sulfate hydrate. And you're going to be told, heat this hydrate up. The hydrate's a really pretty turquoise blue. Heat it up. It's going to turn a white chalk. It's like translucent. It's gorgeous crystals. They're translucent, turquoise blue. You heat it up. They turn to a white, pale, chalky green. I mean, they look horrible. It's like, ugh. I did that. Now, what's happening there is you're driving the water out of the crystal. And because some of that water is deep in the crystal, in order for it to get out, it's going to crack the crystal as it leaves. So when you do that, you end up with the same salt but without the water. And you're going to be asked to do this 3 times. Now what happens is the first time you're still trying to figure out the procedure, so you're a little slow. Second time you got the procedure down, but this is a 3-hour lab, so by the third time you're pushing. You don't really have enough time to do the procedure right. And so that third time you tend to be less precise in everything. And that means that the value you get tends to be very far off from the value you're expecting to get. And it's also very far off from the average of the other 2 values. And that's why we have certain tests of can we throw out data. Because if we have a value that's very far off from all of our other values, we can do a test to see is this value statistically significant, or can I throw this value out and just say our experiment sucked for that particular measurement. You're not going to have enough measurements to do that with 3, but you can say in your paper, we were rushed, we didn't heat this long enough, or we didn't let it cool long enough, and because of that, this value is not as relevant as the other values. And if it's really far off, then you can say, and therefore we are not including it in our average. It's perfectly fine. But we're showing it to you because we cannot throw it completely out because we only took 3 measurements. So the standard way that this is denoted is you'll have a value that you've measured enough times that you have an average. So that's a way to denote average. Another way to denote average is this. Both of these mean average. And then your measurements, you're going to have some measurements above that average. You're going to have some measurements below. Now, at this stage in this class, I would be perfectly happy with you taking whichever one of those is larger. So take the measurement above that is as far as above as possible, and then take the one that's as far below as possible, and then whichever one of those is the largest, just say that's your error. There is a more formal way of doing that kind of averages that out, but it's not worth going through that in this class because at this point we're just learning about this. So for instance, if I had some masses, so there's 5 masses. Generally speaking, you need 3 measurements to talk about error. You need 5 measurements if you really want to be firm about it. Okay? Now, one of the things that differs if you were to really calculate this correctly, and if you go and look up something called root mean squared uncertainty, you're going to see it's this formula. It's like the square root of 1 divided by n, which n is the number of measurements. Here it would be 5. Times the sum of the squares of the difference between the average and the measurement. It's a complicated formula. That is fine if n is large. And that's actually an approximation. When you first look this formula up, that's the formula you're going to find. And it's actually not the correct formula for that. And it's an approximate formula because if you're looking at 100 measurements, like it's in psychology or social science, there's really not that much of difference between 1 over 100 and 1 over 99. The actual formula should read 1 over n minus 1. But 1 over 100 and 1 over 99, that's not statistically different. 1 over 5 and 1 over 4 is the difference between 20% and 25%. That's a pretty big difference. That's a 5% difference. So when you only have a small number of measurements, you cannot make that approximation when you're calculating truly calculating errors. But for you guys, all you need to do is take an average. I'm presuming all of you know how to take an average. Is that true? We all know add the numbers and divide by the total number of measurements? Okay. I'm just asking, at some point I might end up teaching 101 and I'm not sure they would know. Okay, so the value my calculator gives me is 1.054. I'm going to write the full thing that the calculator gives me for this moment because this will allow me to discuss significant figures. Now, what's the farthest away from that? Probably 1.1 on the high side. So that would be plus 0.046. And on the low side, it's 1.02. So minus 0.034. Okay? And that is a standard way of writing this, if you're keeping track of both the positive and the negative error. Sometimes you have to do that. If you suspect that there is a problem with your accuracy, you might actually keep track of your error above and your error below separately, because if your error above is always higher than your error below, then that would indicate that you've got an accuracy problem. So sometimes you will keep track of both, the above and below. But the way that you would write this for this class is 1.05 plus or minus 0.05 grams. Now, I did a whole bunch of things in that step that I now need to explain to you. Error is only given to one significant figure. Now, significant figures are the values of import. So, for error, that means I need to round those to one number. So if I round this top number to one number, these two zeros are just holding the decimal. They're not doing anything other than telling me that the 4/6 starts in the 100th instead of the 10th. So if I were going to round this would be 0.05. If I were going to round this to one significant figure, this would be 0.03. Okay? Now, the measurement that we took, the last decimal place that you report should reflect where the uncertainty is. So the uncertainty in this set of measurements is in the second decimal place. And that means I must report my measurement to 2 decimal places only. And that's why I've got that written as 1.05, not 1.054. And that's why I was saying my calculator doesn't know about the error. It only knows I gave it these 5 numbers and divided by 5. And it's going to give me that average out to as many decimal places as it needs. But for a measurement, that last number, the last number that you write, no matter where it's at in the decimal, tells you where the uncertainty is. That last number is where you're expecting it to fluctuate if you were to redo the measurement. So I would expect that number to fluctuate in that last decimal place. If I were to remeasure, that's where the change would happen. And that's why the average is rounded to that value. Now, a lot of students, they'll get their calculator out and then they'll write approximately because they're rounding. There is no approximate in that. That 4 has no meaning in that 1.054 because the error is an order of magnitude worse than that 4. In other words, that 4 is swamped by the error in the measurement. So it has no meaning. You don't write it. You don't report it because it doesn't matter how good your instrument was, your measurement wasn't that good. So this value is what's called the place of uncertainty. And when you're just given a measurement, and that's all you're given, you assume that that's the error. So if all you're given, then this is assumed error. Now, if it's really high accuracy, you might assume plus or minus 0.01, but generally 0.05 is a better assumption. If you don't know the group and you don't know their measurements and you know nothing about them, you're just reading this number in a research paper, put a 5 plus or minus 5 in that whatever last decimal place they report, and just assume that that's where the error is, and that's what the error is. A lot of books will say plus or minus 0.04 because if it was plus or minus 0.05, they would have reduced the error by 1 decimal place. But that's nitpicking. This 0.05 is good, okay? And some books will even say 0.9. And that's why I'm like, just 0.5. It's a good middle of the road between those two approaches. So now, if you are measuring if you're making a measurement, that is say I have something that falls right here, and that's all I know about the measurement. Now, ignore the lines on the page. So I'm going to turn. Okay, that's all you have. See, now it looks really different because when you have the lines on the page, it was much easier to make a decision about where it was at. Right. So now you have to visually put those lines, which are called graduations, on the page. So you have to mentally estimate where they are. So this looks like it's sort of in the middle. So I would call this 1.5, but plus or minus 0.1. Okay, because that's as good as I can do. Now, if I turn those lines back on, now I have lines. I have a line at 1.25, a line at 1.5, a line at 1.75. Now, with the lines in place, Now I can write this as 1.5. It's not quite 1.5. And now I can see that, but it's definitely closer to 1.5 than 1.25. So now I can write this as, say, maybe 1.48 plus or minus 0.05. And if I were to add additional lines, I could get better precision. You guys are going to encounter this with volumetric glassware. A beaker, very inaccurate, very imprecise, I should say, not inaccurate. It's also very inaccurate. It's very imprecise too. So beakers are graduated like 10, 20, 30, 40, 50. So 15 milliliters in there is going to be somewhere between 10 and 20. And they are also very inaccurate. If you were to actually put 15 milliliters in and then go weigh that on a balance, you would find that that could be anywhere from like 17 milliliters to 12 milliliters. So beakers are not uber accurate either in those graduations. That's why they only cost like $2. Versus later in the semester when you use a burette. That burette's a 50 milliliter piece of glassware. It's got graduations every 0.1 milliliters. And you'll be able to see between the 0.1 and the 0.2. So you'll be measuring volume to 2 decimal places. Now, the number of decimal places is the precision, but it's not the number of significant figures. That's the one final thing, and then I'm going to hand out some homework and walk around. Well, I'm going to hand out the homework, but I'm probably not going to have you guys do homework. We'll see. I'm going to work it with you, in other words, okay? So if I have a volume 1.4, so a lot of the experiments we do in titration, we design the measurements so the volume is over 10 milliliters. And here's why. Say you measure 8.54 milliliters, and another person measures 12.31 milliliters. So there's 2 separate measurements. Now, I'm going to use this in a calculation. And the calculation I'm going to use it in is not addition subtraction, which depends upon the precision of the number, i.e. the decimal place. The calculation I'm going to use this in is multiplication and division. And multiplication and division depends upon what's the fractional error in this measurement. So because of that, it depends on the number of significant figures, not the decimal place. So this thing, you just count the numbers. So I have 3 significant figures here. This one, 1, 2, 3, 4, has 4 significant figures. And that's a big deal when you're carrying this forward into a calculation. In one calculation, you get to keep 4 significant figures. In the other calculation, you only get to keep 3 significant figures because of where your error is at. Yeah. So when we design experiments for you guys, we try to maximize the number. We try to make sure that the number of significant figures you get is as good as you can possibly get for the instrument we're giving you. And that means that we're making sure that we are measuring to the best of that instrument can measure to. This would be the same as if I'm using so say I'm using a 0.1 milligram balance. And in one instance, I measure 0.456 grams, 60 grams. And in the other instance, I need to measure 0.0046 grams. Now, in this instance, my error in both of these measurements, because I'm using the same balance, my error is there. And that error is, so in this instance, this error is plus or minus 0.0005. In this instance, the error is also plus or minus 0.0005. There are balances that are more accurate than that. That would be an accuracy. You know, is it plus or minus 0.0005 or 0.0001? There's a cost difference between those two. Now, in these two measurements, which one of these measurements do you think is more impacted by the balance error? By the precision of the balance, by the accuracy of the balance? So do you think the 0.45 gram really cares if that fourth decimal place is varying by 5 in comparison to the 46 milligram, the 4.6 milligram? So if I take the ratio of these, here I have 0.0005 divided by 0.4560. Now, I've dropped the units there. This is the first time I'm talking about this, I've dropped units, and that's because it's a ratio and the units are the same, so they cancel. So I have grams divided by grams, so those units cancel. So in this instance, I have 1 times 10 to the minus 3. In this other instance, I have 0.1. So in one instance, the variance that the balance gives is a 10% error on my measurement. So the ratio is 0.1. If I make that a percentage by multiplying by 100%, that's 10%. On the other one, it's 0.1% error in the measurement. So if I really needed to measure 0.0046 grams, I need a different balance. This is not the best balance for the job. The error's too high. Generally speaking, you want an error in your measurement to be under 1% due to your instrument. So a 10% error in your measurement is way too high. At that point, you need a different balance. You need a different piece of equipment. Okay? Now, if I were to look up here, this one has 4 significant figures. This one has 2 significant figures. And those significant figures are kind of telling you that the error is higher. So the more significant figures you have, the smaller your error is. Okay? So that's a good stopping point today for you guys to think about this. Too much math in one sitting does not tend to equate to much learning. So I'm going to hand out these two. Now, obviously, these involve unit conversions. So we haven't covered that yet. And this is our last lecture for this week, so we won't get to that until next week, which means I'm going to be moving the homework assignment dates because this is the homework and this is what I want you to do for homework 1 and bonus 1. And I was already, because my 114 students, they don't have homework until next week anyway. So it was a little bit unfair for you guys to have homework this week. So I was already planning on shifting it, but I wanted to see how much I got covered today. Okay. But I am going to pass this out, and then I am going to show you some of the unit conversions and get you at least thinking about it. Okay. So I will be shifting the homework 1 due date, and that means I'll be shifting homework 2, homework 3, homework 4. So I will be updating the calendar I just gave you. There will still be a quiz on Sunday. We've covered enough material for there to be a quiz. So that quiz will go up maybe tonight, but more likely tomorrow morning, and it'll be due on Sunday. It's 45 minutes of your time. You can do it tomorrow during study, work along if you wish to. It can be your goal for tomorrow's Thursday body doubling work along is complete quiz. Now, when we get to the book I've asked you to buy, which is the guided inquiry book, the problems are going to be harder than the problems in these questions. These are from the chemical connection bonus book, both of these activities. And these activities, they are simpler than the guided inquiry activities, but they're also more applied. They're more applicable to what you would run into in the real world. So I liked both books, but when I had to make a decision about which book to force you guys to purchase, I went with the book that taught more, which was the other book. But I made this one a bonus, that this is the Chem Connections bonus book, because the activities in it are really, really good applied activities. They involve automobile engines and acid rain and environmental chemistry and all sorts of things that are directly applicable to the real world. But in terms of helping you learn the material, they're a little bit less applicable. So, and I didn't, I thought about it. I thought about requiring both of them. But in the end, that's $60. And I was like, well, if I have to pick one, all of the students last semester really liked the guided inquiry ones and said it really helped them learn the material. So we'll go with that one, and we'll make the other one bonus. So that's how that got decided. Now I will tell you in teams, for those that are going to watch this lecture later, it's not going to show the flip to teams, just so you know, because I don't have that screen set up. But I will tell you in Teams, there's this interesting video channel. In that channel right now, there are 3 videos called Mystery of Matter. These videos walk you through what we're going to cover in Chapter 2, which is the discovery of the elements on the periodic table, the development of the periodic table by Mendeleev, and then the discovery of radioactive elements, and then the discovery of the elements in the F block, the transuranium elements. These videos are superbly done. They are interesting. They are fun to watch. You will learn a lot from watching them. These are also, for those of you that didn't buy the Chem Connections workbook for bonus, I told you that there would be other ways of getting bonus. This is one of those ways. These are 3 videos that are worth watching. I will post a sheet where you analyze the videos, where you give the title and who was the announcer, and you say what you learned and what questions you have from those videos. And that's a bonus, just like the Chem Connection bonus. So it's another way to get your 100 bonus points, get up to your 100 bonus points. So for those of you that don't buy the optional bonus workbook, this is another way to go about developing bonus. And these 3 videos, toward the end of the semester, I'll be posting a similar video that I pirated. Those 3 I didn't pirate. I'll be posting a similar video that I pirated that funnels on thermodynamics. But these videos are really good videos. I think you'll learn a lot. and that's why they'll be bonus. I will also be posting if you want to attend seminar. I'll be posting the information about seminar. It's on Mondays. That's another way to get bonus with a very similar type sheet to these videos in terms of getting those bonus points. And I was told by our person who handles the Alchemy Club that they're arranging for a tour of a museum by one of the museum scientists. And as soon as she has the dates for that, I will post that because you guys can attend that for bonus. So the Alchemy Club, they do a whole bunch of different things. They do some demos. They do like a Halloween demo show and things like that. And attendance to those things as they pop up is another way to get bonus. I can't give you the schedule for that because I get them about a week before it happens. So I will give you the schedule as soon as I know the schedule. But they also do like trivia nights and watch NCIS nights and laugh about the science and all sorts of things as part of that club. So once I know what they're up to, I'll let you know. The other final thing that I wanted to let you guys know about is oh crap. Really? So there's two places to get peer tutoring at Queens College. One is the Learning Commons, and that's in the basement of Kylie Hall. The guy that runs that was a chemist, Alan Edmond. I taught him, so he's a good chemist. But to get hired as a tutor from the Learning Commons, you have to have a B plus or higher and be recommended by a faculty member for tutoring in that subject. But it is paid tutoring. So keep that in mind. You guys might get invited to tutor. Beta Delta Chi is the Chemistry Honor Society. Again, you have to be invited to join that. A faculty member will recommend you to the head of that. The students that are currently involved in it will check you out and talk to you and see if you're suitable. And then you go in. What they're really checking to see is, are you reliable? Because Beta Delta Chi, which stands for Best Damn Chemist, you have to have a B plus or higher in the chemistry courses to stay in it. It's an honor society. And it is also a service society. So you have to tutor a certain number of hours per semester as part of the requirements for staying a member of that honor society. So they have a tutoring schedule on their website. I will post a link to this. Some of them do online tutoring. Some of them do in-person tutoring. They haven't updated for spring 2026 yet, but they'll get that up in the next week or so. And that's another resource for tutoring that you guys can reach out to as you need it. Okay? The biggest, most common mistake students make in this course is you're shy about admitting that you're struggling. And I understand that. All of us have egos and we all have pride. So you're shy about admitting that you don't understand, and you're hesitant to come and see me during the 3-hour office window to admit you don't understand. Now, part of the reason why I set that 3-hour window on Tuesday, Thursday is I am autistic and I have ADHD. So like if I've got my calendar in front of me and I'm sitting at Teams and I'm uploading stuff and I'm doing streams and I'm posting this and I'm posting that, it took me a huge amount of effort to get my brain ready to do that. And I'm in a flow state and I'm doing it. And then one of you pings and pops a question. And if I answer that question, that completely breaks me out of that flow state. And it doesn't mean that I'm going to be able to transition right back to doing that. I can usually do it if one person asks a question while I'm in the middle of it. If two or more people ask me a question, you can forget it. It's gone. That's it. I'm done for like 3 hours. I'm not touching that for 3 or 4 hours. So what I was hoping, and it seemed to work last night, is if I set aside 3 hours of time that I told my brain, during this time, you are there for the students. Yes, you also have goals you're trying to get done, but those goals don't supersede answering student questions. If that would make me a little bit less tetchy, a little bit less snarky when I got questions. And the answer is it did. So I was much more pleasant when answering you guys' questions during that time because my brain was already expecting to do that. So that 3 hour window on Tuesday, Thursday is a perfect time if you have questions to ask and you're not going to get my worst. Because I don't intend to snap at you. I really don't. And I'm really careful about that. But man, if I had worked hard and it had taken me 2 hours, 3 hours to finally quit procrastinating and finally get where I'm sitting at this computer doing what I'm supposed to do for you, and then I lose it, it's like, oh, well, God, I'm annoyed. And I'm not really annoyed at you guys. I'm just annoyed. You can be annoyed without being annoyed at somebody. And if I were really going to classify it, I'd say I'm annoyed at myself because I know I'm not going to be able to get back to doing that. I know it's gone. So that's my burden to bear. But by setting aside those 3 hour windows, I've reduced the impact of that burden on you guys. Okay? Or at least that's the goal behind that. The other thing to know is I am recording these when we meet in person. So if something, the only days that you absolutely should not miss this class, especially if we're going to swap to being able to submit homework electronically, are exam days. Do not miss exam days, okay? But if you have something come up and you need to miss this in-person class, just make sure when you're on campus, you pick up the homework if I haven't posted it up at the desk. And just do your homework and we'll get along and watch the lectures. And you guys have been watching the lectures. I can see the YouTube. You guys have been rewatching these things. So, just make sure you stay caught up on the material and we're all good. Now, if I start coming into class on the days we meet and nobody's in this class, I'm going to quit recording. Okay. So if I have to drive into Queens College and work, some of you need to be in this classroom to keep me company. That's all I ask. Some of you show up to class. You can even coordinate with each other and say, okay, who's going to show up to class this week? As long as I got 10 people in the room, I'll be fine. But generally speaking, yeah, I'm serious. Generally speaking, as long as I have 10 people smiling at me, I can push on through this. But if and you'll get more out of it if you come to class because there's less distractions. But if there's an emergency, big snowstorm or something happens and you really need to miss class, I can't hold you to a higher standard than I hold myself to. And the reason why we have Wednesdays that are online and not in person is because I have to be with my family. I'm an only child. My mom is a cancer survivor and my dad is 75. So there are just certain weeks that I have to be somewhere else. And the department wanted to pioneer online stuff. They knew I'd be willing to learn the software to do it right. And that allowed them to keep me teaching freshman chemistry, which is what they need, because otherwise I'd have had to take a sabbatical and then they wouldn't have me at all. So it allowed them to keep me teaching the course I'm good at, and also allowed us to pioneer, let's see if we can make this online thing work and if the students like it. So you're going to be asked later on, after you've done this for a little while, would you take an organic class this way? Are there other classes you would like to see done this way? Because we're still getting a feel for this. We know other CUNY schools are doing this, but we haven't been doing this. So is this something that students want? So that's what's going on. And that's why, there may be, even though we're scheduled for in-person classes, there may be instances where I just say, I'm sorry, guys, we're swapping this class to online. And it's because an emergency came up. My mom's cancer reappeared and I've got to be in Tennessee. That happened last year in around this time. My mom's cancer reappeared in her brain. And I got told right as I was walking in to teach, I'm like, I'll be there tomorrow. And I put the phone down and I taught. And then I just went home and packed and headed the next day. I'm like, we're swapping to online for a couple of weeks. So that's what it's like when you have a family member with cancer. You don't know what the next scan shows. So cross your fingers. Keep hopeful. Her scan's next week. Uh, so anyway, we are good. Look over this homework. It is unit conversions. I will probably set up a podcast for tomorrow on that, but we will certainly cover unit conversions on Monday. Now we're Yep, one's homework, one's bonus. Make sure you have both the homework and the bonus.